project-based computational chemistry. That's it.
Yeah, it's bad.
Thank you for coming. I don't remember your name. Would you please remind me?
I'm a new graduate student.
Uh-huh.
Name is Razak.
Razak? In chemistry, physics, or
Chemistry.
MNT? Okay.
This fall I am.
Oh, okay. Yeah, welcome. Yeah, I think if you just audit and sit with you, are welcome to. Even if we do not have any relations in the future, we partially help you to survive in the advanced PChem survey in the spring semester.
Thank you.
Oh, no, no.
My favorite. We could do that actually, make it RGB. Make it a big rainbow. Rainbows are. I love the oranges. This could be. That's the orange. Thanks.
Many thanks to the authors of the homeworks for submitting in time. I appreciate it. Hope that you can survive the little homework during Wednesday. Please remind me, I want to send materials that may help, and I will do them as in the last time. And it does contain directly some answers on the if you just glance through. So, but no answers, no hints for the stuff that you selected by your review for the test exam due next month. Okay, so I will run a campaign for projects maybe on Wednesday. So get acquainted with this test exam so that you know what you choose from. And right now, if you have seen the slides, we can rename the course. It's not physical chemistry. It's history of Nobel Prizes in physics and chemistry. And one of these Nobel Prizes was to Roy Belver for called coherent state. And this word clicks nothing for physics audience, or for chemistry audience, and even physics audience as well. But if we deal with harmonic oscillator, we know that there is a natural width that corresponds to the ground state. And we keep in mind that before quantum theory, oscillators were oscillating, right? So one may want to see how the quantized oscillator performed the semi-classical oscillations. So coherent state is nothing but what we already did in class, like setting up a momentum or initial elongation of interatomic bond, with assuming that this bond corresponds to a quantum particle, and look how it oscillates. So this seems like a very simple problem, right? But there was a Nobel Prize in physics in 2005 for solving it 30 or 40 years ago. So we are on the right track. And the technical mathematical tools that we will apply today would be to find eigenstates of annihilation operator. So I will give additional comments right now, since we are in the middle of semester, basis on some foundations and background. So we applied annihilation operator to the ground state and got nothing to find ground state. And now we will apply annihilation operator to an arbitrary state. This is an anchor in this adventure movie for a hero to climb to the tower. I will just introduce this little trick, and then after we go through it, you will see that it will directly connect to oscillator. Okay. I'm just trying to look back what if needed. Probably I can go directly to slides. I really love to do like interview interactive style, but right now it looks more or less straightforward. If I feel that I don't have energy to speak, I immediately switch to interview mode and ask you guys to help. Yeah, so we are close to finishing chapter about harmonic oscillator, and we will go to angular momentum and hydrogen atom as soon as we are done with it. This is what we look forward to on Wednesday, and I'll skip this stories about possible projects, but I'll try to talk about it on Wednesday. So here is the gentleman who got the Nobel Prize for just focusing on harmonic oscillator, and he was applying it not only to chemical bonds but also to the electromagnetic oscillations in the resonator in lasers, but equations are the same. So just what they would. And here's the concept of coherent state in Wikipedia. So if you look through this article, you will get better and more detailed information that your humble instructor could convey in any reasonable time. So it's better than in a textbook. Wikipedia in natural sciences is reasonably good. So, favorite image of Emma. So this little anchor is our mathematical attempt to find eigenstates of the annihilation operator, and as we get hands onto this procedure, we will see that it will be a really good model to oscillating interatomic bond and several other examples of harmonic oscillators that we will one of the in the past. So if we anytime let me know if you get bored or if you think that you lost track, I will happily return to old-fashioned board or to interview style. So, oh, maybe it's time to go to interview style. Wait, what do you see on the board?
Operator acting upon a wave function that gives an eigenvalue that also acts on a wave function.
That's perfect. Thank you. Yeah. So, yes. Any criticism or friendly corrections to a colleague?
I wouldn't say the eigenvalue is acting on the wave function. I would just say it's associated with the wave function after we apply the operator.
Okay, but how? Yeah, thank you. But how the solution should look like? What are you looking for? It looks like a garbage on a screen that created to irritate young minds with too long equations to read. Can we dissect it and formulate what we need to find? How will you see the answer? If this is a problem, if like I'm enclosed in a box and told that you will not exit the box until you solve this problem, and I really want. So what do we know and what we don't? What is known and what is unknown? How do you interpret?
We know our initial wave function,
Or
just our wave function in general.
no. What is this it's not a trap question. What do we denote by cat? You do. It's my failure that I didn't instruct well how to communicate the idea, but I'm sure you know what it is. So what is this, which chapter are we covering? Yes, and the name of the chapter, okay. Do we know eigenstates of harmonic oscillator? How do we know them? Yes. No, but wave functions, eigenstates. You can write psi sub n, right? Can we instead use a bracket notation? Okay, let's return and ask what is a wave function or
Our
yes? So those will be eigens, like if you have Hamiltonian of harmonic oscillator, we act on the eigenstate, we get energy of this eigenstate. And this notation is just because we do not want to torture each other and write long equation for this function, right? We kind of know what is under there. Okay, let's thank Kaiden. Spencer, can you please continue? So here is the question that I want to clarify for myself and for everyone. How do we solve this equation? What is known and what is unknown?
So you know like what's CN and NR as just kind of like the general functions, but you need to define what how many terms you're summing. Or what your like N is equivalent to, like N1, N2, N3.
Yeah, no. Yes and no. Please repeat. I may misheard. Do we know C sub n?
You know what like C is, but N is going to be like, it's going to be like a power or like a term.
Yes, but do you know, like, can I write C sub n equals and write an explicit equation?
Yes.
What it is? What it is?
It should be a wave function.
But how does it look like?
Drawing a blank here.
You don't need to be precise, just generally, like, is it like sine, cosine, power, exponential, 1 over something?
It's gonna be like a sine, like some form of like a sine wave.
Okay, and what is in the brackets?
Hamiltonian, or no, H bar.
So I'm on your side, but we can go into wrong direction. So here is the trap question which will help us to reveal the truth. Does C sub n depend on x, or it does not?
Was not.
Perfect. This is important. Although we haven't done, it is a really important comment from Spencer about him. This was correct. And what was, I would respectfully disagree that we do know C sub n. Maybe you guys know, I don't. So for me, it is the main task of at least next 10 minutes, maybe the whole meeting. So to find what are C sub n. So n is we understand that n corresponds to sub n, and then it will be normalization factor, Hermitian polynomial, and then e to the power psi x squared. Right? And I'm very lazy to explicitly write what is Hermitian polynomial. So it is either 1 or x or 1 minus 2x squared, and then it goes to power n. And then the normalization factor also, it's like 1 over n sub n over case, 1 over square root of n. And psi is square root of mass, omega frequency, and all this junk. So n does, this one does depend on x. it's an eigenfunction. But when we speak about expansion over eigenstates, so we assume that function, basis function is known, but expansion coefficient, which does not depend on x, many thanks, Spencer, it depends only on n, but it is not known. Depending on about sines and cosines, when we speak about particle in the box, yes, there are sines and cosines. Here is harmonic oscillator. Instead of sines or cosines, there are these harmonic oscillator functions, which are like 1 peak, 2 peaks, 3 peaks, right? So we need to find C sub n. C sub n is a way to store wave function in discrete space. And we are looking not for any wave function. And we are not looking for eigenfunction of Hamiltonian. If we would look for eigenfunction of Hamiltonian, we already got them. We have them, right? Hamiltonian harmonic oscillator and this many hump camels, right? We need eigenstate of the annihilation operator. So here we do know operator, right? It is kind of what we were doing before. So it's we know each symbol here. Brian and Kent of the eigenstates of oscillator, factor, summation, everything is clear. We know what is n. We do not know what is C sub n, and we do not know what is eigenvalue. So we do need to find this C sub n coefficients. The limited optimism comes to us because we do have the same C sub n on left and right. And we may get some mathematical relations by applying and not applying operator on left and right. We will have connection between senior and junior C sub n. But we want to find C sub n as function of n. I should be able to memorize it, but I do not trust my memory. So and we will find it together. So it will be very, very approximate. I will erase or even maybe stop recording. So it should be something like minus n squared over square root of n factorial. And if it's not exact, I'm going to erase it immediately because there should be factors, there should be some things, but we are looking to get an answer in this functional form by solving this central equation. And if we solve it and do additional considerations, we will be able to resolve any dynamics of any natural system that oscillates. For chemists, primarily it's intermolecular bond distance, but there are 10 other examples. I'm erasing it so that no one can catch me saying imprecise or wrong things. But the idea is that it does not depend on x. It's just a distinct set of coefficients. Great. A second. Edit. Too much. So, do you have anything interesting on the top line? Or it is literally what we got in previous slide that we discussed, right?
It's just, yeah, I'm just reproducing the
Yes.
operator.
Yes. So we do need to roll down here to just apply our favorite tricks that we did before. So I can put summation and C sub n upfront because it is neither operator nor wave function. So the rule of thumb is that one must keep order of brass and cats, right? And summations, all fluffy little things can be put factorized in the way we please. So now we keep k and we keep k minus 1. It is an independent index because we want it to be general, not in a sense of rank, but general. So what happens when k meets n and they are Brian cat? Yes. Who wants to? We have a. Please remind your name.
Razak.
Razak. So we have a new attendee, new visitor, Razak, and he would enjoy if someone will help us to explain why n k times n is a delta.
So,
Just visual.
oh, on the board?
Or on a screen.
All right.
Thank you.
So you want me to do a grade or?
Just do a funny image that will convince everyone.
Okay, so. There's k times n. This basically means that we're taking the integral over all reals of phi k, phi x, or phi n rather, sorry, dx. So this finds where these functions are compatible. Okay. So basically all this integral is doing is finding where these functions are compatible. And these functions are only going to be compatible for specific values of k and n. And it's going to make a really sharp peak with infinite height and one area under the curve. And this only is true for values of k equals n. So this limits the mobility between k and n. So if we have k and n right there, and then we have a job delta, how we do that? K, n. The only value for which this is 1 is when k equals n. So what we can do here is we can cancel off one of our sigmas, cancel out our delta function, and just write it as k, and then delta function. Actually, well, we can just kind of port it over as k, and then k, because n has to equal k. This equals 1. We just cancel this off, and then we have our expansion terms in there left over that we'll have to solve for. But basically, this is just checking compatibility between the indices. So it's like a switch function. If k equals not n, delta function equals 0. That's all this is saying.
Okay, well, thank James. Razak, did you become more happy, or you still do not?
Yeah,
Huh?
it's okay.
Okay, thank you. So, and what happens if this delta function meets a summation? It parses one value. So everywhere where we had n, we replace it by k, right? Yeah, yes. We do not have any explicit factors, so it was already k, but we did have c sub n. So because of this delta function, we replace it by c sub k. And the delta function and summation over n disappear. Yes? If there are doubts, let me know if you disagree or not sure. Yes? Okay. So, do we believe in yellow box? Class of 2003 believes in yellow box. Summation over k, c sub k, square root of k, and then k minus 1. Did I lie anywhere? No. We just literally followed the algebraic rules how to process these equations. And on the right, we didn't change anything. So what did we get? How do we interpret this expression? Summations means many terms, right? So it is a series. Term number 0, term number 1, term number 2, term number 3. To compare them, it would be really comfortable if you would have the same index, right? And if you want to put number n here, I want to practice my mathematical liberty. But liberty always has borders, right, by laws. So the index in here and index there differ by 1, right? So if I want to replace k minus 1 by n, it means k equals n plus 1, right? So I do plug it in here. So if I do this change for basis function, then I need to make changes for factor upfront and for expansion coefficient. I'm asking for your authorization. Yes? Okay. And now we do have two summations. Both are over n. Both use the same basis functions. And here is the logic. I was hating my instructors because they assume that it is self-evident. Maybe, but one needs to think about it, to focus. So two series are equal if each term is equal. Maybe there are some other distributions when they're equal, but at least when each term is of the same index is equal, then it is sufficient to say that two series are equal. And if the basis functions are the same, it means that this equation, this two series will be equal if we will have square root n plus 1 times c n plus 1 will be equal to mu times c sub n. Yes?
You cancel off the sums and the cats.
No. I feel myself back in undergraduate school. It is, everyone assumes it's self-evident. No, I cannot cancel. If you want to do it literally, we need to multiply it from the left by another free bra with number m and make sure that we convert this operator times equation into times wave function into just numbers. If you want to do it very, very literally.
Well, you canceled it off in parentheses.
It cannot cancel wave function. It would be. I don't like it. It's philosophically wrong statement. It may interpret what we did, but we just make sure that coefficients by the same order basis functions are equal. It's a little longer statement, but then it is less chances to get criticized.
So by multiplying by a ket
on each side or a bra on each side, you effectively cancel it out.
Yes, yes,
Okay. So you just multiply by bras.
yes. Then we are safe.
Okay.
But I am seeking for your approval of this little statement. Yes? Okay, so how do we interpret it? What does it mean? Is there a smart word for this mathematical property? When junior is equal to senior in terms of rules of progression.
Stagnation.
Okay, that's a really good hypothetical term. I would admit it, but unfortunately, the terminology already exists. We just want to guess and then follow traditional. I don't know how to bring the right word, how to play Wheel of Fortune for this. When you go on the path and then you return back to your original place, or when you go in cycles, is there a way? Or someone who does programming, if you did some Perl. So suppose you have a subroutine, and then the subroutine calls itself. How programmers can call this trick? Recursive? Yes. So it was designed not by programmers, it was designed by mathematicians, but it is a recursion relation, right? So it's like a snake, it's its own tail, it's the object like loops to itself. The object n+1 depends on object n, right? And it means that if we, by any luck, if you know the object number 0, we can immediately reconstruct the whole progression. Because number 1 will depend on 0, number 2 will depend on number 1, number 3 depend on number 2, number 4 depend on number 3. Well, you can continue the progression. And then we can just write it in divide left and right with this part. As James called it, stagnation. Actually, recursion. So the senior is equal to junior, but with some factor. So it will be less and less depending on junior, right? So since it divides on square root of number, the higher the number, the smaller is influence of the lower order to higher order. So just looking at this equation, we see that it should converge and get smaller and smaller and smaller as you get to higher orders. Hopefully. Because otherwise it will diverge and will be mathematically painful. So we agree with an idea in yellow box. I do not see other choices. We'll just assume that we know C naught and then go from there. How would we get C naught later on?
Going backwards.
I will. You know the anecdote. I do not demand to be the first who tells it to you. Windy, stormy, rainy night. A pedestrian walks a dog, and then suddenly a balloon with a traveler settles in front of him, and scared traveler tells, "Please help! Tell me where we are." The person with the dog thinks for a minute. Because certainly you are on a balloon. And then the wind takes the balloon away. And then there was a second traveler in the balloon and tells, we didn't found where we are, but I can certainly tell that we were speaking with a mathematician. Why? First, he was thinking before speaking. Second, he gave absolutely correct answer. And third, this answer was absolutely useless. Well, you were correct. So, rule of thumb, the number of unknowns should be equal to the number of equations, and then one can solve, right? So we should have an additional equation that would later, I have it in slides, I just want us to discuss, that would help us to find C0 and generally find this eigenfunction. And you all know what it is. It's like human memory is like a librarian with a little drawers who can pick up the answers, but sometimes this librarian is sleepy or the keys are rusty, so it takes longer time. So which condition is imposed on the expansion coefficients or on any good wave function?
Has to sum up to 1.
Now it is useful. Let thank James. This is our little strategic plan. So we will guess just as a symbol C0, then ramp up all senior coefficients, and then we will apply normalization condition that C is I absolute value squared, summation over from 0 to infinity should be equal to 1. And since all terms will have a C0 as a factor, we will solve for C0. Okay? Okay. It was just preparatory.
Yes.
So here is our plan for a few more meetings. We do want to solve time-dependent Schrodinger equation. We want to see how atomic body is oscillating if it is quantized. And we already solved time-independent Schrodinger equation. We know this eigenfunctions. And we do have a third way to predict future and find observables, but we are missing expansion coefficients. So we have a little side note. By this trick, this eigenstates of annihilation operator, we will find expansion coefficients that we will plug into here and then find the dynamics and observables that could be of our interest. So we are not doing an exercise on our own mathematical pleasure. We're just preparing to follow the main stream that we already get acquainted and we solved several times. So we just need expansion coefficients for this equation. When I cannot give guarantee that we will complete everything in this meeting, but general direction is that we will find this C sub n coefficients. So it will be eigenvalue to the power n and then square root of factorial. And then we will be able to identify that accumulation of phase can be submersed under this n power. And then I'm going too far. It's not literally, I'm just overarching. We will see that eigenvalues of annihilation operator can be thought as time-dependent eigenvalues. And they will just rotate, oscillating time. And then we will come to this concept of oscillating the given state. So do not expect to have a clear vision immediately. It's only a little traffic light showing the direction. So I may have the same slide in a little better calligraphy. Yes. So here is the box that we all agreed on. Stagnation or recursion, right? So the more senior term is equal to more junior. So if you plug n equals 0, it will be mu divided by square root of 1, right? No jets. Now, if you plug in n equals 1, C2 is C1 mu over square root of 2, right? But C1 is already this little stuff that we can plug in. So it will be mu over square root of 2, mu over square root of 1, C0. So mu squared over square root 1 times 2, C0. Yes? C, if you plug n equals 2, then number 3 will be mu over square root of 3. But number 2 comes from here, right? So it will be mu over square root of 3, mu square root of 1, 2, so mu cube over 1, 2, 3, C0. And then if we dare to continue the progression, it will be mu to the power n divided by square root of all natural numbers from 1 to n. So, no tricks, I was not lying, it's just applying recursion. Right? Approved? So, and now we need to find C0. We are not going to roll backwards. We are going to use normalization conditions, right? Well, I do not need to convince you that wave functions need to be normalized. You believe in this. So, let me double check if we have better calligraphy. No. Okay, then. But I see the light at the end of the tunnel. I think we can arrive to a good point in the remaining 3 minutes. So, our common belief and expectation. If you take expansion coefficient of the order n with and without conjugation and make summation over all integers, we should get 1, right? So we are plugging in index number n is mu to the power n square root of n factorial C0. And here we just, because we want to be very cautious, we put conjugation. Who knows, maybe this eigenvalue is complex. Then we can put out of brackets this C not with and without star, right? Because it's absolutely the same factor everywhere. And then we do have mu star mu to the power n divided by square root of n factorial n factorial.
It's like E.
Yeah.
Anyone wants to object? Do you approve what he told?
I want him to explain.
Oh. And you can either speak or use this one or use
No, he didn't.
empty slide. Okay, do whatever you.
Okay.
Empty slide.
Sure. I'll just write the. There. Okay, so.
From 0. From n equals, yes.
So that's our Taylor series for e to the x. Now, if we go back a slide, we have this mu naught or mu star mu term. In the power to the, or in the top to the power n over the square root of n factorial, which is just n factorial squared, cancels off the square root, giving us the mu terms to the n over n factorial, which if we just take this sum over infinity, returns us e. And since mu star mu is just going to be absolute value mu squared, if they're complex conjugates, we get e to the absolute value mu squared as this little expansion part here.
Yours?
Yeah.
Approved?
I like it.
Okay, thank you. One thing. So, and after, so one equals C naught star C naught E mu squared, or absolute value mu squared, right? Then we can solve for C, if C naught squared will be e to the power minus mu squared. Right? And then if we plug this, oh yes, and then if we need C naught and we assume that C is real, then one is gaining factor 1/2. Okay, I think the time is over. Let's stop here. Please give me a favor and symbolize the end of the meeting. Yes. So I'll stay here and answer any questions, and look forward to seeing you and your homework on.
Why do we put it over to?
Because we were studying for C naught squared, C naught star, and C naught, and we need C naught.
I don't think you agree if we don't get it.
I want you to give evidence.
Yeah, are we walking outside?
Why?
If you do things.
Oh, yeah. Okay.
You don't want
I
to.
understand.
No.
I'm down.
Thank you.
I got Peter like bad enough to like stay here.
Yeah, welcome.
I gotta watch
Just keep going to this class and labs, and it will be counted as vacation.
But I have another relation going on right now, so it's okay to.
Yeah.
I'm gonna go ahead and send you my homework over email.
Super. Yeah, thank you. Yep.